You are standing on a railway platform, feeling the ground tremble beneath your shoes. The vibrations are subtle at first, a deep rhythmic shiver, but then grow more insistent, almost as if the earth itself were aware of what is about to happen. In front of you, a steel leviathan comes to a halt, its massive body seeming to devour the sunlight around it. This is no ordinary machine. It is a modern freight locomotive, a true titan of industry, weighing over 200 tons. Inside this armored beast roars a 16-cylinder diesel engine capable of producing more than 4,000 horsepower. As the engineer pushes the throttle forward, the engine responds with a deafening roar, a sound that vibrates through the platform, through the soles of your shoes, and reverberates deep inside your chest. Black smoke shoots skyward from the exhaust, are twisting and curling into the air, a visible manifestation of the raw power contained within. The locomotive begins to pull a line of freight cars behind it, together weighing an astounding 15,000 tons. Slowly, inexorably, the train starts to move, overcoming the sheer inertia of its own immensity. Your brain, conditioned by years of experience driving cars, motorcycles, or trucks, jumps to a seemingly obvious conclusion. You think this enormous diesel engine must be connected to a gigantic gearbox, which in turn rotates massive axles, ultimately transferring power to these colossal steel wheels. It makes perfect sense, doesn't it? After all, this is the basic principle of nearly every motorized vehicle you have ever known. The engine produces rotational motion, which is mechanically transmitted to the wheels. It seems logical, but it is entirely, completely, utterly wrong. What you are witnessing is one of the greatest illusions of industrial engineering, a deception so perfect that it has operated in plain sight for decades. That engine roaring with unbridled fury, that iron giant spewing smoke and fire, has absolutely no mechanical connection to the wheels moving the train. Zero. Not a single gear, not a single drive shaft, not a single clutch links them. If you were to cut the locomotive in half, you would see that the diesel engine is completely isolated from the rails. Calling this machine a diesel locomotive is almost a misrepresentation. In reality, what you are looking at is a rolling power plant, a mobile factory generating immense energy in real time. But why would engineers go to such lengths? Why not simply connect the diesel engine to the wheels, as is done in heavy trucks? To understand this radical approach, we need to dive deep into the physics of extreme motion and confront a mechanical enemy of unmatched ferocity: friction at startup. Imagine yourself as an engineer tasked with designing a clutch and gearbox for this machine. On one side, you have a diesel engine capable of producing enormous rotational force. On the other side, you have a 15,000-ton train sitting completely still. In a car, when you slowly release the clutch, a friction disc slides against a flywheel, allowing the engine and wheels to synchronize their speed before motion begins. It is a smooth process, easily controlled. Now imagine trying to scale this principle up to a freight train. At the exact moment a mechanical clutch attempted to couple the spinning diesel engine with immobile wheels bearing 15,000 tons of mass, the results would be catastrophic. The friction would generate an unimaginable amount of heat almost instantly. Clutch discs would weld together, melt into liquid slag, or explode in showers of molten steel. The torsional forces alone could twist forged steel axles as though they were made of taffy, all before the train moved even a single centimeter. This exposes a fundamental truth about internal combustion engines, including diesel. They are inefficient at low speeds. A diesel engine needs to spin at hundreds of revolutions per minute simply to remain running, and it must approach its maximum RPM to deliver peak power. A freight train, however, requires the exact opposite. It demands maximum torque precisely at zero speed, at the moment of starting. What is the only machine capable of providing its maximum torque from a complete stop? The electric motor. Herein lies the secret of the locomotive. Beneath the gleaming exterior, the machine operates in three interdependent stages. Stage 1: energy generation. The massive diesel engine, known as the prime mover, burns fuel to spin a shaft. But this shaft does not drive the wheels. Instead, it turns a colossal alternator, converting mechanical energy into electrical energy in real time. This is no ordinary generator. It is a device the size of a small van, spinning at incredible speeds to produce an immense flow of electricity. Stage 2. Energy distribution. The electricity generated flows through heavy, insulated cables to the heart of the locomotive, a sophisticated system of inverters, rectifiers, and controllers that regulate, condition, and distribute the power. In modern locomotives, the alternator produces alternating current, which is converted to direct current, and then reconverted to variable frequency alternating current. This allows precise, almost surgical control of the locomotive's immense power. Stage 3. Traction. Finally, the electricity reaches the traction motors hidden within the wheel assemblies. These are compact yet incredibly robust electric motors designed to endure relentless abuse. When energized, they create powerful magnetic fields that apply immense rotational force directly to the wheels. There are no clutches to burn, no gears to twist. The train begins to move with an almost supernatural smoothness, effortlessly overcoming the weight of thousands of tons, while the diesel engine continues to operate in its most efficient RPM range, untouched by the mechanical stress of moving the train. This separation between engine and wheels not only solves the problem of starting the train, but also provides a solution to an even more dangerous challenge: controlling the train on a descent. Imagine a 15,000-ton train hurtling down a steep mountain slope. Relying solely on traditional friction brakes would be catastrophic. The enormous heat generated could melt brake shoes, warp or fracture steel wheels, and inevitably lead to derailment. The solution is dynamic braking. Electric motors can also act as generators. On a descent, the engineer reverses the controls. The traction motors, once used to drive the wheels, are now spun by the train's momentum. These motors generate electricity while resisting rotation, converting the train's kinetic energy into electrical energy and slowing it down without any physical contact between metal parts. No friction, no overheating, no sparks, just controlled electromagnetic resistance. Where does all this electricity go? It cannot be sent back to the diesel engine nor stored in batteries. Storing such colossal energy would require batteries as heavy as the train itself. Yet the system works flawlessly, demonstrating a harmony of physics and engineering that allows a 15,000-ton behemoth to move, stop, and descend mountains safely and efficiently. In essence, what you are witnessing is the perfect synergy of diesel and electricity, a mechanical illusion that makes the impossible seem simple. And the roar of the diesel engine, the black smoke, the immense vibration under your feet, it all suggests raw mechanical force. Yet the true magic is invisible, conducted through wires, magnetic fields, and carefully controlled currents, proving that sometimes the greatest power lies not in brute strength, but in the clever manipulation of nature's laws. If this journey through the hidden mechanics of the mighty locomotive fascinated you, imagine what other engineering marvels are waiting to be uncovered. From the invisible power of electricity to the colossal forces moving entire mountains of metal, the world of machines is full of secrets just like this. Don't miss out on exploring more incredible stories of science, technology, and innovation. Hit that subscribe button now and join our community of curious minds, because the next discovery might just change the way you see the world.